So today we are going to see uh, the second way of handling a deadlock, that is by using deadlock avoidance technique. So in deadlock avoidance, where the system has some additional information. So additional a prior means before before checking whether that system is in deadlock or not, it has some information about that system. So what are all the information it uses? So simply the model, in the simplest case, each process will declare a maximum number of resources it needs. So before, uh, whenever the system model we will take, we will have a snapshot of what those processes require. So it declares maximum number of resources it needs. Then we will apply deadlock avoidance algorithm. So before giving any resources to that process, we will check whether in what way we can allocate those resources to them processes. So that a circular wait should not happen. Okay, so that is what the main criteria. Then the resource allocation state is defined, means we will have a process sequence such that if that sequence is followed, a deadlock won't happen. So that is what our deadlock avoidance. So deadlock avoidance, where we will get a sequence of processes. If you allocate a resources in that fashion, deadlock won't happen. Okay, so what that deadlock avoidance algorithm uses, it uses a algorithm called as Banker's algorithm. So actually it is a resource allocation algorithm, but it is given a name as Banker's algorithm. Why that name? Okay, so that name is chosen because whenever if you take a banking system, there a bank never allocates its available cash in such a way that it could not satisfy the needs of all its customers. Means it will first see how much amount it can pay to the customer, so that that available cash is distributed among all those customers which are actually requesting. Means if you want to go and withdraw cash, and there might be a person who is actually depositing, so it has to take care how much is deposited and how much it is being withdrawn. So maybe they can put a maximum cash per day you can withdraw in the ATM, like 20 or 25,000. Or if you want more cash, you should go to the bank and first ask the bank request, then only we can withdraw. So that is what the procedure. So in the same way, if that bank doesn't have that much money, so it won't allocate, so they won't give today, maybe they will give it tomorrow. Means that resource, that money as a resource is given to that process, means to the customer, such that deadlock won't happen. Okay, so that's why they are avoiding a deadlock. Okay, so that same algorithm, so we are applying here to our process. So what are that things we will use? Okay, so it must declare, means a process whenever it enters the system, it gives some information like maximum number of instance. So what instance? Each resource type, like a process, it needs different resources such that a printer or maybe a keyboard or maybe a typewriter, whatever, different kinds of resource types. So it should ask these many instances of resources of different types I need. Okay, so I that is the need, and how much is the maximum I need. Okay, so whenever it requests those resources, then our algorithm will determine how much is actually allocated and how much it needs. So uh, whenever it requests, then the system must determine whether we need to allocate these resource, so that it should be in a safe state. Otherwise, the resources are not allocated. If it is in the safe state, we will allocate. then it will be allocated. Otherwise, what we will do is we will wait until a process releases enough resources. Okay, in the same way how our customer went to the bank and he asked like 5 lakhs he needs, but today the bank is not allocated that much amount. Maybe tomorrow that resource is given. In the same way, if the request is given, if the resources are available, it is allocated to that process. Otherwise, it must wait. Okay, so waiting is actually okay instead of making other process go into the deadlock. That's why the name given as deadlock avoidance. Okay, so what that algorithm? So before going to that banker's algorithm, first we will see what are the data structures we are using. So data structures are available resources for each process, means the number of available resources of each type. Okay, so if available of j is equals to k, means available of j, maybe take example as 3, means there are 3 instances of resource type rj. So rj is given for each instance. Okay, there might be 3 instances. So k instance of each type is available. Okay, so like printer, 5 printers are available, keyboard 3 available, maybe a scanner 2 are available. Like k is given for each resources. Okay, then max. So maximum is defined as a matrix. Okay, why? Because there is a process one. So we'll see why it is declared as matrix in the when we take example. But you just remember matrix, it defines maximum demand for demand of each process. Okay, so whenever it is equals to k, then it may request that much amount of instances, okay, of resource type rj. That's why rj is indexed based, because there can be different types of resources. Okay, so there might be processes, that's why indexed I. Then allocated means before going into that system snapshot, there are some resources already allocated to that process. Means allocation of ij is equals to k, means I have allocated like 3. 3 means the process pi is allocated with k instances of each resource type. Maybe I have allocated printer 2 printers, means k is 2 for resource type rj printer. I have allocated 1 scanner, means k is equals to 1, and the resource is scanner. So that is how it is given. Then we have to calculate the need. Okay, so need is it is it indicates the remaining resource needed for each process. Okay, so it will request this much amount, this much resource I need so that I can complete my task. So the need is also given as like if it is equals to k, means it needs k amount of instances. Like it has allocated 2 printers, but it needs another 1 printer to get the work done. Okay, so that's why the need is calculated as the maximum resources it needs minus already allocated. Uh, think that it maximum is it needs 3 printers, but actually it has allocated only 2. So need is 3 minus 2 is equals to 1. So we'll see with the example how these data structures are actually we will use in our algorithm. Okay, so these four are the data structures we will use. Now we'll see with how the algorithm works. Okay, the algorithm is given as a safety algorithm. So safety algorithm is used to check whether we are entering into the deadlock or not. Okay, so at the end we will get a safe state of that system. So first there is a work and finish. So work is nothing but uh, available resources, and uh, finish is nothing but whether that process finished the task or not. Okay, so initially we will take the available resources into that work, and all the processes are initially initialized with false, means they have not finished at all. Now we will take each process one at a time, from indexed I, so starting with the 0. So since all are uh, initialized with false, so if it if the process is not completed its task, then finish of I is equals to false. Means the first process is still not executed, completed the task. That's why we'll check how much need the resources, how much that process needs the resource. If it is less than work, means if it is less than the available resources, then we will allocate. Okay, so we will allocate the the available resources such that it should execute its work and finish off that process, means finish off the zeroth process is true. Then go to the step 2. This should continue till all the processes executes. Okay, so that's why it went to the step 2, and again it has went to finish off. Initially it was 0, now it is went to the next process. It will continue such that if no such I exists, means all the processes have completed its task, then finish of I becomes true, then we will end the state, end this algorithm. So finish of I becomes true, then we will tell system is in safe state. Maybe in some scenario, the condition won't becomes true every time, means the finish of one process becomes false in whatever way, then we will tell the deadlock will happen if you follow any of the sequence. Okay, so before allocating a resource, we are checking what is the state, means I'm just getting the sequence how I should how the resources should be allocated. Should I allocate with first process, second or third process, or should I change like first, third or second? We don't know. So in the same way the sequences will come after executing that algorithm. Okay, so the resource request, actually this is the banker's algorithm, where again for any request, whenever a process makes a request, it will first taken it as a k instance, whether how much instance it needs. Then if the request is less than the need, means need is nothing but it is like need is less than available, then it will go to the this step, and we will have available becomes available minus request, then allocation, we will allocate those many resources to that process, then the need of the process is less than the request. So actually we don't need these things when we see with the example, you will understand how actually this is working. Okay, so if the at the end we will get a state, safe state, then we can allocate in that sequence. Okay, so we'll see with one example how actually this algorithm is applied and how we can get a safe sequence.